Let us move on to a different example. That is the scattering from a small and perfect conducting sphere. So I can erase the board, blackboard. So in that case, the incident electromagnetic wave will scatter from a small perfect conducting sphere, and conducting sphere will have polarization and magnetization. So we have incident wave, it has E and H, and H is perpendicular to that. So the scatter has radius A, and the conductor is perfect. What will happen? So we have the following. So basically, the electric field and magnetic field component of the electromagnetic wave will polarize with the electric dipole moment and magnetize with a magnetic dipole moment, and they will oscillate in time with the same frequency. And what are these things? In chapter 2, I think, you studied that the isolated conductor under the uniform electric field. What you do, you can solve either Laplace problem in chapter 3, or you can use the image problem. So you said that there is one charge here and the other charge here, and there's the image here, q prime, and it is the image here plus q prime. You find this. You find that the electric dipole moment of the conductor you can find easily because you have the image charges or you have the surface charge distributions. So basically, the electric dipole moment of the sphere is 4 pi epsilon 0 a cube times the external electric field. In our case, the external electric field is the incident electric field. And what is this? We are saying that some incident polarization, amplitude, and the phase of the wave. And this will be oscillate in frequency omega, which is the same frequency of the electromagnetic wave. This is trivial. And how about that the magnetic dipole moment of the perfect sphere, for perfectly conducting sphere? What you can do? So we are talking about the perfect conducting sphere. You worked at the magnetization of the hard sphere or permanent magnet sphere, ferromagnet sphere, in the following fashion. So you put the sphere which has the magnetic permeability mu to the external magnetic field, and you calculated the magnetization. So for vacuum, the magnetic permeability mu 0 in the matter, that was mu, and your magnetization was 3 over mu 0, mu minus mu 0, mu plus mu 0, B external. So, but this was for a material with some magnetic permeability. If it is a perfect conductor, what is the mu of the perfect conductor? For perfect conductor, what is the mu? Basically, what should be? For dielectric sphere, what is the dielectric constant for the sphere is perfect conductor? So what is the limiting value? So basically, D is equal to epsilon E, and in here, B is what? Mu H. So when epsilon is greater, electric field goes to 0. This is the case, limiting case in a perfect conductor. For that case, B goes to 0 in the perfect conductor when mu goes to 0. So for if you pick up the mu is equal to 0, you will obtain that the magnetization of the perfect conductor. So the value will be what? M will be minus 3 over 2 mu 0 B. If it is a perfect conductor, if mu goes to 0, B goes to 0, how we can say that the magnetization? How we can say that the magnetization? What are the boundary conditions? One boundary condition, N dot B should be the same. So N dot B inside and outside should be the same. This is the perpendicular component. So when inside this is equal to 0, therefore N dot B have to be 0. But the tricky part is the tangential component. What is the tangential component? N cross H out minus H in is equal to surface current density. This is the tangential component. So inside the sphere, if you say that this have to be 0 because you know field here, then you will end up with what? Surface current. And that surface current creates the what? Magnetization. Okay, magnetization of the sphere. So from the boundary conditions, you can see that there should be some surface current, and that surface current creates the magnetization, even if the sphere is a perfect conductor. So other thing, we can write that the magnetic dipole moment of the sphere just multiplying with the magnetization with the volume. So that should be equal to magnetization, that is minus 3 over 2 mu 0 times the volume 4 pi a cube. Because the magnetization is constant, you can integrate through the volume easily. That is nothing but 4 pi a cube times B incident. So 4 pi over 3 a cube. So what I am saying, the 4 pi over 3 a cube is the volume of the sphere. So 3's will be cancelled. That should be minus 2. And you have mu 0, B over mu 0 is the H incident, and that should be the following. So you can put the oscillatory term here, minus I omega t. So M, magnetic dipole moment of the sphere, have to be minus 2b 2 pi a cube times what? B over mu 0, that is H incident. So basically what we are seeing, that electric dipole moment of the sphere, that is 4 pi epsilon 0 a cube E incident, is along the direction of the external electric field, that is the electric field of the incoming electromagnetic wave, and magnetic dipole moment is minus antiparallel to the H incident. So, and what is the relation? M and P are mutually orthogonal to each other, because the electric field and the H are mutually orthogonal to each other. So these are the sources of the scattering. And what we are going to do, we will try to calculate that the scattering cross-section per Salt angle from a perfect conductor using the full expression. Full expression was scattering cross-section per Salt angle k to the 4 divided by 4 pi epsilon 0 E0 square, polarization after the scattering dot electric dipole moment, plus n cross polarization after the scattering dot product magnetic dipole moment, divide, take the absolute square. Again, what are our incident fields? E incident is incident polarization, amplitude of the oscillation, e to the I ik n0 dot x, and H incident is n0 cross E incident over impedance. If you want to calculate that this first term, this is the easiest one, that will be what? Electric dipole moment is here, 4 pi epsilon 0 a cube, and E incident and is there, and that will be equal to 4 pi epsilon 0 a cube E0 e to the I k n0 dot x n0 dot x. The initial polarization epsilon 0 dot the polarization after the scattering. That will be the first term. So let us work on with the second term. Let us work on the second term. So for the second term, let us say this is the first and this is the second. For the second term, n cross epsilon complex conjugate dot m over c is equal to n cross epsilon complex conjugate dot m is nothing but minus p a cube h incident minus 2 pi a cube h incident over c, and h incident is nothing but n0 cross e incident, so that will be equal to n cross epsilon complex conjugate dot, so take the coefficients here, minus 2 pi a cube over c, and h incident is nothing but n0 cross e incident, and e incident is nothing but that term. So instead of e incident, I have what, 1 over z0 here, cross n0 cross h incident, and h is incident nothing but epsilon 0 unit vector e0 e to the I k n0 dot x. So what are these things? So let us play with the coefficients. I have 2 pi a cube, here I have 4 pi a cube, e0 and e0. When I take the square of this, that will be cancel this e0, and the rest is this coefficient. What is that coefficient? That is nothing but square root of mu 0 epsilon 0, and the other is this goes as a up. 1 over c is equal to square root of mu 0 epsilon 0, and 1 over impedance is equal to epsilon 0 over mu 0, and mu 0 terms will be cancelled. That becomes epsilon 0 goes out as a epsilon 0 square, and that will be cancelled with that term. So altogether the scattering cross section per salt angle will be the following. So we have k to the 4 power divided by 4 pi epsilon 0 e0 square, and from the first part of the expression we are e0, from the second part we have the e0, take out the parentheses as a e0 square, which will be cancelled that term, and we have square root of mu 0 epsilon 0 times square root of mu 0 divided by epsilon mu 0 over epsilon 0 over mu 0. So mu 0 terms will be cancelled. That will be epsilon 0, and if you take out, that will be epsilon 0. Only difference will be the 2 factor, and you can write the rest as 4 pi epsilon 0, and you have a cube square. So then leftover terms will be epsilon complex conjugate dot epsilon 0 from the first one, and from the second one n cross epsilon complex conjugate dot product n0 cross epsilon 0. And with a minus sign, that will be minus, and the difference will be with a factor of 2, minus 1 over 2 n cross epsilon complex conjugate dot n0 cross epsilon 0 complex conjugate. Take the square of this. So this bunch and that bunch will be cancelled, and the scattering cross section per salt angle will be k to the 4, again we have the k to the 4, a to the 6, and the rest is epsilon complex conjugate at epsilon 0 minus 1 over 2 n cross epsilon complex conjugate dot n0 cross epsilon 0 complex conjugate. So if you take the 4 parentheses, that will be minus 1 over 2. So let us try to calculate this. Let us try to calculate this. Let us again separate the parallel cross section, sketching cross section per salt angle parallel to the sketching surface and perpendicular to the sketching surface. You have k to the 4, a to the 6. So for the parallel one, so take the geometry again is the same. You have the incident wave and sketching wave lies on the xz plane. And if you are looking at the epsilon dot epsilon 0 parallel to the sketching surface, what will be your result? Which are parallel to the sketching surface? This is epsilon 0. After the sketching, this goes down on the xz plane by amount of theta, like before. Therefore, epsilon dot epsilon parallel to the sketching surface will be nothing but, again, cosine theta. How about this term? What is n0 cross epsilon 0? Epsilon 0 is along x-axis, n0 along z-axis, n0 cross epsilon 0 along y-axis. That is before the sketching. After the sketching, what is this? N on the xz plane, and epsilon 1 is again on the xz plane. If you take the cross product, again that will be along y-axis. So therefore, this will be 1. Therefore, result will be 1 over 2. And take the square of this. And I told you that the incident wave is something like this, 1 over square root of 2, epsilon 0, 1, epsilon 0, 2. Therefore, you will have, from the square of this, you will have the 1 over 2 factor, weight factor. How the situation perpendicular to the sketching surface? K to the 4, a to the 6 you have. So for that term, before the sketching and after the sketching, epsilon will be along y-axis like before, so that will be 1. Only a difficult one, that will be the difficult one. So you will do the what? You will take the n cross epsilon 0, n cross epsilon 0, n0 is along the z direction and epsilon 0 along y direction, which is the perpendicular to the sketching surface. N cross epsilon 0 here is inside the blackboard, and after the sketching you have this cross that product, and that will be differs by theta. Therefore, that cross product will be differed by amount of theta, and you will obtain from that scalar product a cosine theta. And you should include the weight factor here. So again, we calculated that the sketching cross section per salt angle perpendicular and parallel to the sketching surfaces. Now, let us calculate the total sketching cross section per salt angle and the polarization, and discuss about the results. So after a trivial algebra, you can calculate that you can sum of them. And if you sum of them, if you sum of these two terms, you will get the following: k to the 4, a to the 6, 5 over 8, 1 plus cosine square theta, cosine theta. This is for total sketching cross section per salt angle. The important thing is the degree of the polarization, and that was the definition of what? Perpendicular minus parallel divided by total scattering cross-section per solid angle, and you will get 3 sine square theta, 5 1 plus cosine square theta, so something else. So let us plot this something else and see the difference from the scattering from the dielectric sphere. So if you plot this, you will obtain the following. First, let us plot the degree of the polarization as a function of angle. This is forward 90 degrees and backward, and this is cosine theta goes in the other way around. If you send an electromagnetic phase which is unpolarized, when angle is 0, that will be unpolarized, and this function has some maximum, and that maximum is somewhere around 60 degrees. This is something is cosine 60 degrees. So not in the 90 degrees like a dielectric sphere. So you can obtain a 100% polarization, some different angle, this is 1 at around 60 degrees. And another interesting result, you are expecting to see that if you look at that the scattering cross section per solid angle as a function of angle, you will see that the scattering is increased when the angle cosine theta is -1. So basically this is the function of this, and that represents a what? Strong backward scattering. This is expected. If you send the electromagnetic wave as a sphere, so strongly it will be reflected back because it's a perfect conductor. So along the 90 degrees, this backward and forward scattering per solid angle will be antisymmetric. You will have a strong backward scattering but less forward scattering. And if you integrate through the solid angle, all solid angles, you will get the same similar order of magnitude from the as you obtained from that dielectric sphere. So these are the two examples related with the scattering from the dielectric sphere and perfectly conducting sphere. The trick is the same. Scatters will induce some polarization and magnetization. Using this, you can calculate that the electric dipole moment and magnetic dipole moment. And you can calculate that the radiating fields and treat that as a scattered fields. Then you can calculate that the scattering cross-section per solid angle. All scattering cross-section per solid angle formulas related with the k to the 4 with the omega to the 4th. That means that there are more scatterings at high frequencies. That is the basic reasons we are seeing the sky as a blue. We will discuss this on Wednesday. But what we did the things for only one scatter. Practically, we have several scatters. So what happens if you have the collection of scatters? So what we are going to do? We will do this general approximation using the Maxwellian theory, but before going to do, let us crudely investigate what we have to do. If you have several scatters in the medium or collections of scatters. So if you have several collections of scatters, when you send the electromagnetic wave, so each will be scattered from the scatter centers. So that will have some n0, and after the scattering that will have some n4, and here that will be some n0, and then that will be some n if you have a collection of scatters. So each points here will behave a oscillating electric and magnetic dipoles and induce their own radiations, and we will see them as a scattering. The situation is the following. At each point you have scatters. They are basically electric and magnetic dipoles. So if you generalize this formula over there, the approximation is the following. Approximation is the following. Instead of one scatter, you have several of them. So basically, if you have a collection of scatters, you will have the following format. You have the sum of all contributions of all scatterings. So you have epsilon, the polarization after the scattering, from the dipole of J, and you have the other contributions. So you have the magnetic dipole, and you have several of them, and after the scattering each of them, you have the sum of all contributions. So sum up them. If you do this, do we do correctly or not? If you sum up the scatters contributions from individual scatters and sum and take the square, do we treat this formula correctly or not? Actually not, because all waves here after the scattering will do some funny things, interference and diffractions. Okay, we have to take into account that, and basically we can take this into account by introducing a phases, and this will come naturally when we study that the scattering as a general theory from the Born approximations in next time. So basically the situation will be the following. So let me define that for one scatter you have n0 and n. What is the change in the wave number? So basically all scatters here, scattering we discussed so far, the wave number changes directions. Okay, so the magnitude of the wave is same, but the direction is changing. Okay, so you have incident wave number kn0, and after that you have kn. So we will call this as a q vector. Q vector defines that the difference of the wave vector before the scattering, after the scattering. And if you have a j number of scatters, that will be j. So basically you can write this as I q, this is the difference of the wave number, dot at any location scatter j. So take this in the parentheses and multiply this one. Now this piece here has a name which is called a structure factor, and it could be used solid state in crystals and so on. I am not going to in detail, but let us move on one more thing. If all scatters are distributed in different places, but the values of the electric dipoles and magnetic dipoles are identical, then you can say they are the same. No needed for the summation. So then you can write this whole stuff as a following form. Scattering cross-section per solid angle, scattering cross-section per solid angle for one scatter times the square of this e to the I q dot xj square. And this is called f of q. The name is structure factor. So if you have a collection of scatters, but let me tell you again, this expression will come naturally when we study that the scattering using the general Maxwell theory. Means that we will write that the wave equation and solve the wave equations if we have some perturbations in the medium, and that will come naturally. But at this point, I can tell you the following: if all scatters are random, like in the air, in the atmosphere, the sum of this number of scatters, very simple, sum of this. But if it is solid, like quartz or transparent solid, and if the incoming wavelength is long relative to the lattice spacing, there won't be a scattering. It will be passed through that. Okay, so basically, if you have a uniform structure, so uniform structure, and the wavelengths are very long relative to that, so that will be pass. Okay, there won't be a structure. If the wavelength is short relative to the lattice spacing, there will be Bragg structure, Bragg scattering or diffraction, okay, like X-rays in the solids. But if they are all randomly oriented, the structure factor will be the number of scatters. That is the case we are going to use. So if we write that the f of q, so summation through the j e to the I q dot xj, this structure factor will be the number of scatters for random distributions of scatters. If the scatters are not randomly distributed, if they are crystal structure or some lattice structure, you have to define that the new structure factors. There is one in your book for the cubic lattice, for example. If the wavelength is very long relative to the spacing of the atoms in the lattice, you don't see a scattering. So the scattering vanishes everywhere except forward direction. It can go forward like a transparent quartz or transparent rock. But if the incoming wavelength is short relative to the lattice spacing, then you have the Bragg diffraction or scattering and so on. But we are now concentrated on what? Long wavelengths relative to the scatterings. But our aim to explain to the blue sky ray light scattering. So in our approach, which we are going to do next time, we will have random scatters in the atmosphere, molecules in that atmosphere, and the contribution of those to the scattering will be only n number of scatters. So if you have n, then the scattering cross-section per solid angle increase by a structure factor by n. So next time we will write the Maxwell's equations, wave equations, including some perturbative terms, and we will solve using the Green's function again, and you will see that we will find this kind of formula naturally, including this structure factor. Okay. So next thing is to include that many possibilities scatters in the medium. Today's examples for only one scatter. Then we said that by hand we can include the effects of the interference and diffraction effects by including some phase here. And if all scatters are the same as an electric and magnetic dipole, we can write this in this format. And if the scatters are randomly distributed, this summation is nothing but the number of scatters. If regularly oriented, we have to be careful. So that's all for today.